is Physics 2212 Lab 3 Circuits. So the purpose of this lab was to predict the behavior of circuits containing resistors in series and parallel, use multimeters to measure the actual values of conventional current and the potential difference in the circuits, and examine the behavior of ohmic resistors and capacitors. A quick preview of our findings was that we found that the 47 ohm resistor had a potential difference of negative 0.96 volts. The 100 ohm resistor had a potential difference of negative 2.04 volts, and the current was 19.1 milliamps, and the charging time was 2 seconds, and the discharging time was about 40.95 seconds. The fundamental principles in this lab was the node rule, loop rule, and Ohm's law. The node rule basically states that what goes into a node is equivalent to what comes out. The loop rule is that the total voltage around a loop is 0. And Ohm's law basically states that voltage is current times resistance. Predicting currents in I1 and I2. So for part 1 of the lab, the system was the circuit and the surroundings are everything outside the circuit. And the conditions are 2 1.5 volt batteries, 2 ammeters, and 2 resistors in series, one 47 ohms and 100 ohms. Now we're going to replace an ammeter with a voltmeter. This basically allows us to read the entire charge of the circuit via the voltmeter, which it reads to be 3 volts coming from the two 1.5 volt batteries. Add those two together, makes sense. And now, due to the voltmeter's high resistance, the ammeter now reads 0 on this specific circuit. This then allows us to find the voltage drop around the circuit via the loop rule. If we add the voltage of the batteries to the voltage of both resistors, the voltage drop from both resistors, we can find that we know the delta V of the battery to be positive 3 volts, and via the experimental value that we found for I in part 1 that the ammeter showed us, we can figure out the voltage drop for the 47 ohm resistor and the 100 ohm resistor being 0.96 volts and 2.04, both negative volts, respectively for both of those. Now this is a graph representation of this circuit. Essentially, we see that points A and B are from the two batteries, and in that little column we see that there are 2 jolts of 1.5 volts representing each battery, adding to the total 3 volt circuit. As we continue along, we see that the 47 ohm resistor drops slightly in voltage, whereas the 100 ohm resistor drops far more in voltage, which lines up with both what we found and what we theoretically predicted. And then the circuit continues as expected. For part 2, we created an RC circuit, which is essentially a resistor-capacitor circuit. So the system was that, and the surroundings are obviously everything outside of that circuit. For this one, we kept the 2 1.5 volt batteries, but instead now we have a capacitor and 2 light bulbs. This part of the experiment was testing the time to charge and discharge for the different light bulbs. So for the 10 ohm light bulb, this is the 10 ohm resistance in that light bulb. It took around 10 seconds for it to charge. And for 20 ohm light bulb, it took around 20 seconds for it to charge. Possible sources of error for this is an imprecise stopwatch, or dim, or an old light bulb. That was the one we were using, and not being as accurate. So finally, discussion. So what if we charge the capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Essentially, if there was no resistor in the capacitor, or if there's no resistor, the capacitor would charge almost instantaneously. Obviously, this is extremely unlikely to happen in real life because things like batteries, resistors, light bulbs, etc. in a circuit cause resistance. Therefore, nothing would be perfectly allowing it to charge like instantaneously. Additionally, the measure's time would be larger than the predicted due to the fact that we predict batteries as if they're smaller than in reality. Essentially, batteries are still charge has to move through them, but in prediction models, they're usually a point or smaller than they truly are. Thanks for listening.